Welcome back to the morning show. It's time for Wise Guys Wednesday. UofI professor Paul Kwiat is telling us how to determine the color of something using our eyes, a prism, or even a grating. Take a look.
Hey everyone, good morning. Nice to see you again. When last we met, we were trying to figure out, or I asked the question, what color is this neon light? It's a little bright right now, but most of you, I guess, have seen a neon light. And the question is, what color is it? And in fact, we're not going to answer that today because I realize we probably need a little bit more background for the answer to make sense. But today I want to discuss, well, how do we know what color anything is? So if I just quickly share my screen here. So light, just to review, we know is an electromagnetic wave. And if I have bluer light, it'll have shorter wavelength, and redder light, it'll have longer wavelength. But how do we actually know what color something is? So there are a couple different ways that we might know. So one way is that we use our eye. So of course, light comes into the eye, it's focused onto the retina in the back of the eye, and that retina has different photoreceptors, actually 4 types of photoreceptors. They're the rods, and those don't really detect color. They're good for low light, but not for much else. Here's a picture of the rods, which are here indicated in green, and the cones indicated in purple. But there are actually 3 types of those cones, and those cones each detect a different range of wavelengths. And so if I want to know what color, when I look at something, what color I actually see, it's going to depend how much each of these photoreceptors are activated. So for example, if green and red are activated about the same, I'll perceive that as something that's yellow. Just a quick aside, it turns out that some animals like birds actually have 4 photoreceptors, 4 types of photoreceptors, and in fact, they can even see into the ultraviolet. Okay, but with the response for our photoreceptors is pretty broad, so it's hard to get really precise determination of color. Another way that we could do this is we could use something just like a prism, right? So the way prisms work is that as light goes from one material where it's at one speed into a different material where it's at a different speed, it will bend, assuming it comes in at an angle. And how much it'll depend will depend on what the difference in that speed is. So the velocity is given by the speed of light divided by the so-called index of refraction. The bigger the index of refraction, the slower the thing is moving. And in this case, the more that the light will bend. And it turns out that the speed that light goes through different materials like glass or water depends on what color it is. And typically blue will refract more. That's why if I look at this prism, the blue is bent more. But there's not a really big difference between the blue and the red. It's maybe only about 5 degrees in a typical material like glass. So it's hard to get a big spread. So we want to look at something where we're going to get an even bigger spread, a difference between the different colors. And that's going to rely on interference. So light, we said, was a wave. So here's a wave on top. And if I add 2 light waves together and they are lined up so that the crests are lined up with the crests, they will add up. I'll get constructive interference. I'll get a big wave. And if instead they're offset from each other so that the crests hit the trough, then they'll cancel. And that's destructive interference. So I have here just a little simulation where there's light coming in from the left and it's going through 2 openings. And we're just going to show what happens when that light propagates here. We see that we get regions where I have constructive interference, like right down the middle and off to the side and off to the side here. And then there's some destructive interference between them. Okay, that's with just 2 slits. Let's look at something maybe a little bit more interesting. So something where I actually have, in this case, 10 slits. And if I look up really close, I just see that the pattern is really complicated. It's kind of hard to see what's going on. But if I kind of zoom out and I look further away from that, now we see what happens is, again, I get this constructive interference down the middle and to these 2 side lobes, and then there's a lot of destructive interference in between. So my light is kind of really more, I won't say focused, but collected into these patterns. The main thing that we're going to care about is that different wavelengths are going to diffract different amounts. So shorter wavelengths are going to diffract less. Blue would diffract even less than the green. And now I can get actually a pretty big angle difference between, say, blue and red. So instead of being 5 degrees, it might be 25 degrees, something like that. Okay, so let's just see what this actually looks like then. So I happen to have one of these gratings right here. And you may remember I had before this LED tree. So it goes all the way from blue on one side all the way up to red, and then there's a little white one at the end. I'm just going to turn that on like that. So if I tilt it down, now you can really see a little bit So there's blue on the one side going to green to yellow and then finally to red. And if I look at that with my grating, I'm just going to put the grating right in front of the camera. You see, in fact, that the light that's on the left, the blue light, is not deflected as much as the light that's on the right, the red light. So that's what I said. The longer wavelengths are diffracted more. And we see the white light, in fact, has this whole range of colors. In fact, I could compare this to this is just a normal flashlight. And again, I see that I have a whole range of colors, and that's because that flashlight, the filament in that, as it's hot, the electrons can move at all different frequencies, and they can emit over a whole range of different colors, just like the sun does, basically. So in that case, we get a spectrum, as that's called. It's really this continuous spectrum all the way from blue to red. So basically, it's just all the colors of the rainbow. Okay, so coming up at some point, we will try and understand what's going on with the neon light then. What color is that actually? Until then, hope you guys have a good week. Bye-bye.
And Jack has your forecast next. We'll be right back.